Assalamu alaikum, dear students. In this lecture, I will solve problem number 3.20, which says that consider a physical system which has a number of observable A, B, and C. And we have to find the result of the measurement, means their eigenvector, their probabilities of the compatible observable. Which among these observable are compatible? First, we need to check that these observable are compatible or not, and then find the eigenvectors for common common eigenvectors. Which among the set of the operator A, B, C, A, B, A, C, and B, C form a complete set of commuting operator, and which will be possible if they are forming the common basis. So first, if I go to solutions, so first we will check whether the first two observable A and B are compatible or not. So AB, commutator of A and B will be equal to AB minus BA. So checking A and B, it gives not equal to 0. It means they do not commute, they are not compatible. So for A and C, A are given, C is given, C and A. So this will give us equal to 0. It means these observable commute, they are compatible. A and C are compatible. Similarly, for C and B, B and C will be equal to BC minus CB. So B and C, if we check their compatibilities, this is also not come equal to 0. It means they do not commute. Now we solve the eigenvalues problem for each matrices. For the first matrix A, determinant of A minus I is should equal to 0 for linear independent eigenvectors. This is the secular equation, we also known characteristic equation. This will lead us to the eigenvalues A1, A2 and A3. So both two values are degenerate. It means they will have complete set of commuting operators. So if we solve it for the eigenvectors, which will give A1 is equal to 1 0 0, A2 is equal to 1 1 under 2 this, and similarly for A3 is equal to this. And if we solve for another matrices, for the matrices B, we will determine that B minus B into I. B is the eigenvalues, and if we find its eigenvalues, it will give us B1 is equal to 0, B2 is equal to 2 minus under root 6, B3 is equal to 2 plus under root 6. And we are observing that we will not see eigenvector because the operator does not commute with each other. So we do not have a common eigenspace because A and B are not commuting with each other. They do not have a common set of eigenvectors. Finally, we examine the both observable C. Determinant of C for the C operators. We can find its secular equation, and similarly it will lead to the eigenvalues. C2 is equal to this and C3 is equal to this. So if we find the eigenvector C1, C2 and C3, the only two compatible observable A and C, so their eigenvectors are also A1 is equal to 1, A2 is equal to 1. The first part is the only two compatible observable are A and C, so their measurement yield with eigenvalues A1, A2, A3 and C1, C2, C3. The compatible observable are, as we have mentioned, A and C, and they set up their common eigenvectors. So common eigenvector of A1 and C1 are equals. Similarly, A2, C2 are equal, A3 and similarly A3, C2 are equals. Okay, so if two observable are compatible, it means their eigenvector will be same. Looking into part 2, we have that first A is not common set of commuting operator because its spectrum is degenerate, and B is non-degenerate, so it form a complete set of commuting operators. Similarly for C and A, B also does not form a complete because their operator do not commute, and similarly BC does not form a complete set because the operator do not commute. If the operator does not commute, it means they will not form a common set of commuting operators, or if the eigenvalues is degenerate, they will not form a common set of commute operator. Similarly for A and C form a common set of commuting operator because operator commute.